I'm Ben Jones from MIT, and today, along with Ed Chien from Boston University and Jenny Lin from the University of Utah, we're going to teach you a bit about computational knitting. So the plan for today is first to get everyone on the same page, first about what knitting is, why it's important, and for this crowd, why are there interesting geometry problems in knitting. Then we're going to talk about computer representations for knitting at 3 levels of abstraction: the fabric level, the stitch level, and then the yarn level. And we're going to discuss some of our work at each of those. And then we're going to finish by introducing some interesting open problems in computational knitting that may hopefully inspire you to pick up the needles yourself. So to start, what is knitting? This may be what you think about when you think of knitting, a cozy handcraft that you use to make bespoke items for your friends and family. But knitting is also a large-scale manufacturing computerized process where these high-throughput industrial knitting machines execute knitting patterns very precisely and repeatedly. And these are probably the first kind of knit objects that come to your mind. Everyone knows that socks are knit. You might also know that the fabric that makes up most t-shirts is also knit, just very finely. Knitting can also produce fabric that is soft and stretches, so it's an ideal technique for making clothing that conforms to the wearer, like kind of athletic wear. But other knitted textiles are less obvious. The upper of this Nike shoe is a knit object. In fact, if you look around the average home, you'll find a plethora of textiles, many knit, some woven, that account for much of our built environment. And it may surprise you that knitting finds uses far beyond household textiles. The aerospace industry uses knitting to preform precise and complex composite parts. Knitting can be used to create soft sensors for wearables and robotics. It can also be used to form the actuators for soft robotics. And knitting has recently found wide use in architecture, from knitting formworks for complex concrete parts, complex manifold shapes for whole curvilinear structures, and even actuating buildings like this recent installation at Burning Man. So with this breadth of applications, it's undeniable that knitting is useful, but still, what precisely is knitting? We haven't answered that yet. So knitting is a process for making fabric. On the left, you can see the structure of that fabric close up. Yellow and blue are alternating rows of yarn that have been pulled and formed in these vertical loops. These loops like that, going around that shape. So if you were to pull on these loops from the end, you just get a straight piece of fabric, they disappear. But they don't do that in knitting. And that's because in each row, the loop has been pulled through the loop on the row above it. And that anchors it in place and makes the fabric stable. On the right, we see how this is done in a traditional process in the handcraft. So the knitter is pulling a loop of yarn over one needle, and then that needle is used to poke through loops that are already on the other needle and pull them off onto the one. So you're forming a bunch of loops, pulling them through each other, pushing them from back and forth from needle to needle. So that can be kind of hard to follow in the video, so here's a static shot of the process. On the needles, we have the active loops, they're highlighted in green. These are loops that would fall apart if there were no needle there because there's nothing anchoring them in place. And they're waiting for a new yarn to stabilize them. On the right, we see along their finger this active yarn, which is going to be flipped over into a loop and then pulled through. And then below, we see all this in-progress fabric that has already been stabilized that's kind of growing underneath the needles. So this process is incredibly flexible in what it can make, but it's not exactly fast, as anyone who's knit a sweater can attest to. So for speed, we have industrial knitting machines. These achieve the same basic purpose, making loops out of incoming yarn that stabilize in-progress fabric. But instead of storing many loops on each needle, knitting machines have one tiny needle for every loop and move the yarn between them. These actuated needles are going to reach out and grab the yarn as it passes, creating the loops. So we can see what that looks like here. I'll go fast. So it went around the circle there, those needles all shot out and grabbed it and pulled it down into new loops. So I like this animation because it clearly shows the order and structures of the loops without all the needles in the way. And it also demonstrates the order the stitches are made is important. As you'll see later, guaranteeing that a well-defined stitching order exists is a critical and sometimes difficult to achieve property for automatically generating these sorts of knitting patterns. So zooming out, we can see a modern whole garment machine, which, as its name implied, is capable of producing an entire wearable object like a sweater in one piece. You can kind of see in the center this yarn carrier going back and forth, which is moving the yarn between the needle beds, and there is a sweater coming out the bottom. And on the right, you can see images of those needles shooting out and grabbing. So in order to be a whole garment machine, this yarn is going back and forth and alternately being grabbed by the front, like a bed of needles on the front, that's facing towards the back, and a bed of needles on the other side that are coming in. So it creates the front of the garment and the back of the garment, respectively. So when the yarn reverses direction to form the back of the sweater, it's going to create a tube or a cylinder of fabric. So we can see another animation.
As the carriage moves in one direction, it activates the needles on one bed. And as it moves in the other direction, it activates the needles on the opposite bed.
The other kind of structure, this is one of the two basic topological structures we can make.
Here's the same animation in two...
That's us? Oh, sorry. Sorry about the sound there. I didn't realize that was us. All right. So that's one of the basic kinds of structure you can create in knitting are these tubes or cylinders. The other basic structure that you can create is a sheet or a plane, which is created by just doing this on one side of the machine or just going back and forth between needles in hand knitting. So, for example, a scarf would be knitted flat as a sheet, where like a tube sock would be knitted in the round or as a cylinder. And by combining these sheets and tubes, we can create almost any topology of shape with knitting. So, as a geometer ever, something might feel off to you right now. I've said that we can create cylinders and planes, which are both developable surfaces, things you can fold out of a sheet of paper, and this is enough to create this straight sock, tube sock on the left. But we all know that most socks have heels, they're bent. Yes, knitting is stretchy, but this goes far beyond just stretchiness. This thing has intrinsic curvature, so how is that achieved? So looking back at our structure, there's no hope we're going to get any curvature with this regular grid of stitches. What we need to do to create curvature is introduce irregularities to this grid, highlighted in green and red and blue here, creating a type of singularity that we call shaping. So I'm not going to go into the details of these. Later in the talk, you'll hear a whole lot about shaping, but this is how we get curvature. And so via shaping, we're able to introduce some geometry knitting, in this case, curvature in the heel that we call short rows. Okay, so far I have hopefully convinced you that there is geometry in knitting, but why is it a computer graphics problem? The short answer is that knitting machines are fiendishly difficult to program. Here's an actual knitting program written for a whole garment machine. It is represented as an image where each pixel is an individual machine instruction. So programming a knitting machine with current commercial tools basically amounts to manually writing G-code in MS Paint. It's kind of awful. So just looking at this, would you believe that this program makes the Stanford bunny? I know I wouldn't. So this difficulty of corresponding the machine instructions to the final shape and appearance understates why we would like to have graphical representations for knitting. We would much rather work with something that we can intuitively understand, like a mesh. So that's kind of the motivation for why knitting comes into computer graphics a lot. All right, hopefully now we're all on the same page about what knitting is and why we need graphical representations. And this next section, we'll discuss knitting representations and go into detail about a few of them. To motivate this, let's think about levels of detail that we can view knit objects at. So at one level, a knit object is a fabric. And this has properties like its texture, its shape, its composition out of different patches of fabric. But if we zoom in, we see this intricate network of stitches that make up the fabric and control its appearance. And if we zoom in even further in individual stitches and their connections, we'll see that each stitch is made up of interconnecting twists and turns of yarn. These three levels correspond to our representation levels. At the fabric level, we're concerned about patches of fabric with their connectivity and visual and mechanical properties. If we look closer into the stitch level, we'll see an intricate network of individual stitches and begin to understand that there are a lot of constraints on which combinations of stitches are realizable. If we zoom in even further to the yarn level, we can start reasoning about how these yarns intertwined, and it becomes more mathematically advantageous to think about the topological connectivity to really understand how the high-level properties of a knit object emerge from the arrangement of the yarn itself. All right, I'm going to take some time to go in a very brief, truncated history of some of the knit representation research. So for a long time in graphics, the fabric and yarn level of representations have been familiar in the simulation side, giving us detailed but slow, physically accurate simulations of individual threads versus fast, thin sheet approximations of complex garments and other pieces of fabric. More recently, graphics research has started exploring the intermediate level of representing knitting at the stitch level to try to capture the best of both worlds. One particularly graphicsy way of approaching this is to represent stitches as mesh faces, with each face being typed with the local yarn topology, which allows for recovering the yarn level representations if you desire that. This representation is really good at creating a stitch level knits for modeling, rendering, and simulation, but it's kind of difficult to create fabrical designs with this. Considering the dual of this representation, a knit graph where each node is a stitch, gives us more mathematical tools to reason about fabricability. So this work by Narayan et al. Devised a set of sufficient graph properties to guarantee machine knittability and created an automatic tool to remesh shapes into these graphs. I'm going to highlight briefly one hard constraint, that graphs cannot have helices, which will be a major motivation later in the talk. So by combining the intuitive editability of stitch meshes with the analytical power of a knit graph, these powerful stitch-level editing environments were created that allow designers to create and edit fabricable knit patterns for any given shape. All right, that's it for the history. Next, I want to talk about the fabric level. So stitches aren't the whole story of an object. So take a look at this family that all has the same sweater, you might say. I think we'd all agree that these are conceptually the same design, but at the stitch level, they're completely different. For example, if we zoom in on the hem detail of the two children, we'll see that one is 9 stitches high, while the other is 16. If we were to try to use a stitch level editor to create this design, we need to completely remake it 3 times from scratch. However, if you were to buy a traditional hand knitting pattern to make the same thing, you'd be given one set of instructions that would be sufficient to make all of the sizes. So how come the traditional methods can do this, but our fancy visual editors can't? So this is the motivation behind some work I did at the University of Washington with all these wonderful folks on the design of knit templates. Another way of viewing this motivation is this tension between the inherent customizability of knitting. So look at how these similar pairs of objects vary in size or texture and their composition of how different pieces come together to form the object. And that has a tension between the discrete nature of knitting as individual stitches, which are going to make reusing and modifying patterns very time-consuming and difficult. So to figure out how to square this circle, we asked a bunch of knitters, what design aspects do you think about when you're creating a knitting pattern? And we came up with a list of 7 axes of knit design. Among them are texture, which is how individual types of stitches are combined to create interesting visual effects. Shaping, which is that curvature we talked about earlier. Composition, which is how you take the sheet and tube primitives and put them together to create various interesting topologies. And finally, shape variations, so variations in size and shape, making these different types of sweaters. And a crucial observation about all of these properties is that they're all at the fabric level, they're all high level. There's not a stitch in sight in any of these. So for this work, we proposed a design tool that enables designers to take a parametric model as input and apply some high-level specifications to create what we call the high-level knit template. And from this template, we can generate machine knitting instructions for any variation of that template and shape. There are 2 main contributions that make this possible. One is a new data structure for knit templates that captures these high-level knitting design considerations that we got from the knitters, and a design tool for the creation of these templates. So we'll start talking about the data structure. So we're going to take a patch-based approach to knit design. So our data structure for knit templates is a coarse parametric quad mesh that we're going to call a coarse knit mesh. This duck here is an example of one. The elements of the quad mesh support a variety of labels on them for things like texture, shaping, seaming, and orientation that capture the local properties of the object. And the design of our knit template representation was inspired by 2 key insights that motivate first using coarse patches that allows us to ensure machine knittability, and also suggests that we should use quad patches, and in some ways quads are the right representation for knitting. I'll talk about both of those. So first, why patches? So we chose to use coarse patches because they allow us to verify machine knittability at a high level. So the first insight is that we can lift the low-level machine knittability constraints on knit graphs that we talked about earlier into high-level constraints. So what we found is that there are 4 coarse patch local properties that if you guarantee them, and also guarantee through some means, we don't care how, that whatever you put inside of these is a knittable mesh or a knittable graph, then we can prove that the combination of all of these will be a knittable low-level graph. And the ability to have this guarantee convinced us that high-level patches are a good way to go to have easy editability while also ensuring machine editability. And the second question to answer is why use quads for these? So we use purely quad meshes instead of quad dominant meshes because of this neat correspondence we found between knit design and quad meshes. And we'll describe that using this example of joining these two tubes, of knitting these two tubes that are joined perpendicular to each other. So remember that at a high level, all knit objects are composed of sheets and tubes of fabric. And it's an important design decision, how you're going to put these primitives together to achieve this particular shape. And we call this composition. And for this example, there's two ways of doing it. So in the first one, the shape is made up of two tube structures, one that has a slit opened in it to allow them to join. And then the other, so here we go, two tubes, slit in the middle. And the other one, the vertical section is created of a tube, kind of highlighted in orange, and then a sheet represented in red, and then another tube on top of that. So what's the difference here? Let's clean these up and look at them just as quad layouts. We can see here the difference between these two is in the index and number of singularities where they deviate from pure quad meshes. Their sum is the same because that's determined by the shape's topology. But the combination is interesting. So our second key insight is that common knitting compositions align with specific combinations of quad mesh singularities, which allows us to encode compositions as quad meshes with different singularities that we call composition rules. So composition rules correspond to structures you've probably seen in knit objects before. For example, joining tubes with common orientations in a point, right here, in this pair of pants, or in a seam, like underneath the arm of a sweater in the armpit. And also various ways of closing tubes, like the seam at the toe of a sock right here. These two singularities are right here on the sock. Or the flap at the end of a teddy bear's arm. So we don't expect knitters to know geometry and understand what we mean when we say, oh, we need three valence -1/4 singularities here. But we do expect them to understand these kinds of composition rules. And so using this correspondence, we're able to translate geometry into language that knitters understand. So in our meshing tool, we give designers a menu of 9 composition rules to choose from that correspond to ways of splitting and merging, closing tubes, opening holes, and bounding patches. So one note about these singularities, you might wonder what exactly we mean here. So in this work, we're really talking about fabric level singularities, which are the singularities you'll see in quad layouts, things that are joining the separacies. And these get to be a little bit loose, a little bit flexible about local curvature. This isn't the stitch level singularities that we talked about earlier and that you'll hear about more later. So having a data structure for knit templates is only half the battle, however. We also need a tool for designing them and making sure they're valid. So our system takes as input a parametric mesh. Users are first guided to construct a quad patch layout on which they then apply labels to create a coarse knit graph. And from this, our system can generate machine knitting instructions for any input variation. So any of these shape variations on the left, we can make a corresponding program on the right and knit it. So this design tool needs to address 2 main challenges. The first is designing consistent patch layouts across the whole input family of shapes. And the second is creating correct labelings, so valid coarse knit meshes that are knittable. So first we're going to talk about consistency. So in the patch design phase, making these blank meshes on which to put labels, our system guides users into placing the correct number and type of composition rules to ensure that the topological constraints are met. It also allows you to add optional orientation guidance. So this is used to drive a quad meshing algorithm that is solved jointly across many exemplars of the family. It's a variant of mixed integer quadrangulation. The solving jointly is really important because if you were to just solve this meshing problem over a single example and then try to use pointwise correspondences to take these patches and put them on to the other things in the family, you start getting a lot of these distortions. So in this case, you'll see that if we just used straight pointwise correspondence, you'd get these really kind of curved and stretched quads in the torso in this example. Whereas if we did it jointly, you get kind of more regular and uniform meshing across the whole family. So once we have patches, we need to label them. And in patch labeling, users are going to annotate the patches with information about texture, about shaping, seams, and the other design properties that we found the knitters care about. And the challenge here is in satisfying the constraints of machine knittability. So our solution to this problem is to encode those constraints as SMT equations. This allows us to do a couple things. First, we can immediately populate some initial valid labeling that is knittable right off the bat. The user doesn't have to do anything to get a knittable object. But they're also going to want to customize things. So as the user clicks around, changes properties, our tool is able to automatically do completions and changes that maintain validity while also respecting the constraints that they have just provided. And we have a couple of tricks to make this happen at an interactive rate so users can design things quickly. So this is kind of an image of what we support with this tool. This is what happens locally in each patch. We can support the knit direction, shown by those arrows. The blue line is a seam. This is where fabrics in different directions are joined by sewing them together. We also have these two glyphs in the middle that denote what kinds of shaping are allowed to be used, and also use the designer's preferences and how to distribute that shaping within an element. And finally, the colors used to represent the texture. This is things you might see like ribbing, stripy patterns, stuff like that, that you'll oftentimes see in knit objects. So what can we do with this? So here's a selection of the designs knit from our system. So we can see from here we're able to achieve a variety of texture and shapes. We're not going to have time to discuss all of these, but I'd like to highlight two of them today. The first here is this bear, which highlights the benefits of using composition rules. So stuffed animals are usually knit fairly simply. In this case, a central tube is used that's closed off like a sock toe on the top and bottom, and has 4 perpendicular tubes for limbs that are closed with flaps. So as a test, we tried to create this pattern without using any composition rules, just orientation guidance, just using direction fields, essentially. And it's basically impossible. You'll almost always get warped layouts like this that require seams everywhere to knit. If we apply our composition rules, however, we get a very nice clean layout, which was used to create this bear. And the second example we wanted to highlight shows our system's ability to apply the same template to many shape variations. So here we wanted to knit a child's version of this adult's dress. The child's version needed to be smaller, but also just has less curvature in general. So both these shapes use exactly the same design, so no additional work was needed to get both patterns. And we're actually also able to achieve much more drastic shape variations, like this angled hem in the dress on the right. So to finish, and as a motivation for the next portion of the talk, I'd like to actually talk about some limitations of this work. So you might notice that the quads used in this remeshing are a bit smaller than they really need to be. In an idealized version of the system, you could have just singular vertices essentially, and only use non-singular vertices if you wanted to cut off something for like a different pattern. But since we didn't choose to spend a great deal of time in solving the local curvature problem, we needed to use relatively small patches to minimize the deviation from our input shape. But with a better algorithm for tessellating patches that still offers sufficient control of shaping, this technique could operate at a much higher level and allow even faster, more fluid design iteration. Yeah, and with that, I'm going to hand it over to Ed.
All right, thanks for that, Ben. So I'm going to talk a little bit about the work that's coming out of my lab and looks at sort of the stitch level of abstraction here. So there'll be a bit of repeat of things that Ben has said, but figure it's good because they're sort of central concepts. The stitch level of abstraction, as noted, is sort of characterized by knit graphs or these like quad dominant stitch meshes. So essentially, there's various definitions floating out there. They all differ slightly, but the basic idea is that vertices of your knit graph or faces of your stitch mesh correspond to like individual stitches. And the main aim, when you're looking at it at this level of abstraction, is to achieve like consistent element size. And this is because at the end of the day, as we saw with that sort of like shaped heel on the sock, you kind of want like consistent tension in some sort of rest shape throughout the object to get geometric fidelity. You'll note I mentioned quad dominant mesh, so there are non-quad faces, and these of course correspond to these irregularities in the knit pattern. As Ben mentioned, like if you've only got the regular pattern, if you want to maintain consistent element size, you can only do developable or like flat geometries. So yeah, let me talk through a little bit these irregularities. So on the left here is just the detailed structure, and then on the right here is sort of the corresponding knit graph. We're using the knit graph of AutoKnit, so that's like the specific example that's here. You've got these coarse edges in black, which sort of join the stitches row-wise. And you've got these orange edges, these whale edges, which join the stitches column-wise. And here we have three kinds of irregularities. There are these two increase and decrease in green and red, respectively, and they're whale singularities. And so it's very easy to see in the actual structure, like what's happening here is that there's an incoming column of, or an incoming whale, and it splits into two outgoing whales. And then a decrease is, the merging of two incoming whales. And those are given by triangular faces here. And then sort of corresponding to pentagonal faces here are ends of these short rows. So what are these short rows? These are sort of like partial courses, partial rows of stitches, and you can see that they sort of affect kind of like a bending in the opposite direction, per se. But yeah, I wanted to show that example because like the ends themselves are irregularities in the pattern where you start these like partial courses. Any questions on this? Great. So I wanted to also emphasize that we're sort of in the whole garment setting. And so, maybe we pretend that we've come out of Ben's design pipeline and we've used his composition rules and we know where the seams are to be sewn together and where the holes are that have to be closed up afterwards. Then the aim is to get to figure out the specific knit structure for the rest of the design, the layout, and you want it to be sort of fully machine knittable. I came here with so here's an example of like the simple dress model where there's no post-processing, and then here's two models where we've already specified that there will be these sort of holes to be closed after you come up with the particular whole garment plan for these parts. Yeah, and I wanted to make a definition here for this knitting time function. So this is pretty important. It's just a scalar function from 0 to 1, and it encodes the sort of general direction in which you're sort of building or knitting the surface. And it encodes the dependency as well between the coarse rows because as we saw, you need a row of loops in order to, intertwine the next row of loops into it. Of course, the level sets of the function correspond roughly to the desired coarse rows. And the whale direction is going to be normal to the level sets, so it's given by the gradient. And typically, this is given either as user input or in many cases, the user just specifies where they'd like the knitting to start and end, and you just do like a harmonic interpolation to come up with a smooth function that interpolates from beginning to end. So yeah, this is kind of the way that, or one fashion in which you can specify, given the base like geometry, like what, how in general you want the knit pattern to be aligned, is through this time function. The other point I wanted to highlight for background and speak a little bit more about is this helix-free constraint in particular. So As Ben noted, this is the real hard manufacturing constraint, relevant to both like machine knitting and also like hand knitting. You need to have sort of a path over the stitches, like an ordering on the stitches to be produced. In the knit graph context, this corresponds to having the course rows sort of join up as they come around any cylindrical component. And this is sort of the behavior that you don't want to see, the helicing. This is necessary in the pipeline so that you can do this sort of, there's a step in the machine compilation in the AutoKnit framework called tracing, which is where you take the helix-free knit graph and you come up with this self-supporting yarn path. I will acknowledge that this is confusing, right? Because I'm sure you saw the image of the cylinder, right? And you saw that literally the yarn path does, it ends up, wrapping back around on itself after one go around, so it does helix. But the way that they achieve it here is via this tracing step. So first you come up with something helix-free, and then there are these detailed rules so that when you come back around to a certain point, you will hop up to the next row. And really, I just wanted to highlight that mainly this is like a trick because it's challenging to sort of achieve, quote, like the right amount of helicing when you generate this knit graph. And we'll see that some of our works offer a way to do this potentially. And this constraint, as well as several others that we don't mention, these are kind of difficult to handle in existing pipelines for quad dominant meshing and stripe texturing. So I'm going to talk a little bit about the stuff that we've done, where we've sort of modified methods for stripe generation on surfaces, or for coming up with stripe patterns, with a focus on manufacturing, maintaining some of these manufacturing constraints. This is work that's done. It's been first authored by my PhD student Rahul. And I also wanted to acknowledge lots of the collaborators that we've had from various institutions. And I really want there to be three main concepts from this section of the talk. This is not ours. This was introduced by a 2015 work on stripe texture generation from Knoppel et al. This is these spinning forms for specifying stripe patterns. I want to talk about the global foliation structure and how it relates to sort of maintaining these hard manufacturing constraints. And lastly, I wanted to offer like a philosophy on the stripe singularity placement for geometric shaping, guided by the curl of the guiding vector field. What do striping algorithms try to do? I don't know, you imagine, you're an artist or something and you're trying to render like a zebra or a tiger or something that has some sort of, interesting non-trivial stripe pattern. And these papers aim to sort of allow you to do that via an input vector field that sort of specifies the direction and frequency of the stripe pattern. And we sort of work off, an example is this work from Knoppel et al. And we work off their framework, but here you can see an example in the plane for them. So here you can see that the stripes are orthogonal to the general vector field direction, and when the magnitude increases, the frequency of the stripes increases. So that's sort of an example of how you use the vector field to specify things. Remember I mentioned what we're after is consistent element size at the end of the day. And so this is equivalent to the goal of having evenly spaced courses and whales. And this really is analogous in some sense to having evenly spaced stripes. And we can achieve such stripes by using some sort of constant norm vector field, right? Remember the norm corresponded to sort of the frequency of the striping pattern. And in this bunny, what we did, and what you might imagine doing via the knitting time function is to take the gradient of it and normalize it as a way of specifying the stripes that correspond to the course rows. and you would rotate it 90 degrees for the whale stripes. And here, what we have is an illustration of the problem, I guess, with the naive thought of, okay, so obviously what we do is we generate 2 stripe patterns that are orthogonal, and like, boom, we're done. The problem is that there often are helices in the stripe patterns that result. There's no sort of simple way to guarantee this within the standard global optimization framework that they have. I do want to call out here that this was considered first in a 2021 work, KnitKit, and they sort of attempted to fix things afterwards via remeshing operations. And it didn't come with guarantees. So our approach generally has tried to work within the framework of spinning forms and impose this helix-free condition as a hard constraint with guarantees. And we found in this setting that you can sort of use simple linear constraints to do this, actually. Just to talk through the image a bit, here's sort of like a simple sock model. You can see a green helix here. And the linear constraints are sort of these path integral constraints of the spinning form. And if you impose it, you can sort of kill the green helix and achieve a machine knittable output. And maybe the last high-level thing I'll say about this is just that the first work that attempted this sort of geometric shaping is of course, the seminal AutoKnit work. And they take sort of this iterative, like, front-marching approach that sort of makes it more challenging to incorporate user input into the process. The best you can do is sort of use some of those individual stitch mesh level editing operations that you saw Ben bring up briefly. So we take more of a global optimization approach. Okay, so yeah, the very first point that I thought is interesting, and I hope people take away, is this notion of a spinning form. So stripe patterns, you can think of them as being specified by like a periodic function over your surface. So when the function is in one half of the circle, you color it red, say, and when it's in the other half, you color it pink. And I have some examples of like individual triangles on such a stripe pattern, potentially. These are discretized in the 2015 work as spinning forms. So these are discrete differential one forms. That's a lot of jargon for saying they're a number assigned to each oriented edge in the triangle mesh. And you should think of the value as denoting the change in this function over the edge E. So here I tried to give some examples. So in most of the stripe pattern, there's no bifurcation or introduction of another stripe. So it's all sort of nice locally. And they look mostly like this. Here, I sort of, the orientations are given by the yellow arrows. And here you can see it sort of varies over a single period. So I gave it a negative 2 pi value. Here it varies over a period, so another 2 pi value. And here it comes back down over roughly 2 periods. So I sort of gave this as 4 pi here. And yeah, over such triangles, it's nice. Like this sort of sums up to 0, and you can use sort of a nice piecewise linear interpolant for your phi. Of course, in a stripe pattern, in order to maintain even spacing, you do need places here where you have like new stripes. So these are these sort of singular triangles. And here I just have yet another example. This is a little less than a period here, a little more than a period. So I sort of gave it 1.6 and 2.4 here. And then coming back this direction, it varies over roughly 3 periods. Yeah, and as you can see, if you sort of integrate over the boundary here, it doesn't integrate to 0. So there's no well-defined local function. And you have to use sort of this novel interpolant from their work to sort of render the stripe pattern. So here, I just wanted to throw quickly a reference for DDG. There's several out there, but this is one that's nice from Chien. He's got a course. If you feel like you want to dig into a little bit into what is a discrete one form, And then likewise, what is this funky D1 thing? I'll try to give some intuition here right now, but if you want to know more, that's a good reference. So yeah, in particular, for a stripe pattern, if you have a spinning form for it, it has integer curl on all faces. So what is this D1 operator? Essentially, it's just, you can think of it as a path integral around the boundary for each face, and it's just this oriented sum of the one form going around. And it's going to be equal to some integer multiple of the period, generally, so that you have like a well-defined stripe pattern. I already talked through before, but like we can see here that, as I noted, it sort of sums to 0 here on most triangles, and you have it's nice and integrable locally, and you have like a piecewise linear function over the triangle. And then here, where you have these defects and these like birth and death of stripes, you have non-zero curl, and in particular, like integer curl. Yeah, and we call these stripe singularities. And they correspond to the increases and decreases and the ends of the short rows in the eventual pattern. Yeah, and intuitively, you can also think of it as there's like a birth or death of like 2 pi worth of level sets for the periodic function, if it's plus or minus 1. Yeah, so hopefully that was sort of just the basic intuitive introduction to how do you get a stripe pattern from like a spinning form, which is like a discrete one form with integer curl on some of the faces. Yeah, and I wanted to talk now a little bit about, now we care about sort of the global structure for this helix-free constraint particularly. So you can also interpret these stripe patterns and these spinning forms as vector field flows. So here I tried to sort of illustrate, on most triangles, it's piecewise linear, and the flow is just going to be along these level sets. It's sort of a very simple structure. On the singular triangles, it's definitely more complicated, and down here in the right, I have sort of an illustration in the neighborhood of a singular triangle as to what the vector field flow looks like. I'll talk through the specific structure here in a second. But just to set up this foliation language and these terminology here, the integral curves of the vector field, they form the leaves of this foliation. So the foliation is really just the vector field flow, a fancy word for that. And what is an integral curve? But a curve on the surface such that the tangent is equal to the vector field at every point. Stripes are collections of integral curves. So maybe like, a pi worth of integral curves is a stripe. And courses and whales in the eventual knit graph are particularly periodically sampled integral curves of the foliation. So indeed, we do care about how these integral curves behave. Yeah, and obviously the only non-trivial topological behavior you can see is at these particular stripe singularities. This is my version of Ben's slide about the non-equivalence here of stripe singularities and the quad mesh singularities. So yeah, here are sort of your typical quad layout or quad mesh singularities, usually just valence 3 and valence 5, sometimes more, but yeah. But the problem is if you have something like this, it leads to a disagreement of like the course and whale directions, which is why like in Ben's framework, like if you have something like this, you've got to post-process, you have to like, put it together there, sew it together there at the end. Yeah, you should think of these for, I imagine there's people from the meshing community. You should think of these as being akin to the position singularities of the quad dominant instant meshes framework. So here's an example where you have this triangular element and it sort of leads to a new column of quads here in this part. So this is maybe the best analogy for those folks. So yeah, let's take a deeper look here at this singularity structure. So they're pairs of index plus and minus 1 singularities. Here, I'll freely admit I'm skipping a lot of like basic vector definitions. Let me just mention them quickly. A singularity is a point at which the vector field vanishes. And the index refers to sort of the number of times that the field rotates as you circulate around the singularity. But I'll leave it at that here and just use the picture to sort of roughly communicate the flow structure locally. What you can see here is that essentially your integral curves, your period's worth of integral curves are being like sort of born, you could say, or emanating from the +1 singularity here. And they sort of wrap around and go out in this direction. And here, the blue, you can sort of see the other integral curves sort of like making space for the new ones. And then separatrices here are these integral curves that they sort of separate the boundary between these like newly birthed integral curves and the old ones. Specifically, they're integral curves that start and end at the yellow points, the saddle points. And what's really cool is I dug into the mathematical literature, and I found that people who've been sort of characterizing the topology of vector field flows on surfaces, decades ago, they were doing this, and there's this orbit complex, which sort of is the global characterization of the vector field flow. And it consists of cells that come about when you partition S via these separatrices. So in such an orbit complex, every cell is topologically equivalent, has a flow that's topologically equivalent to a periodic flow on a cylinder. So here, it's just, all the integral curves are just these periodic cycles that run around this cylinder. Or horizontal flows on an infinite strip, so R across the unit interval. And here, the flow just runs sideways. And here, I wanted to give an illustration of what this looks like in this context. I apologize, certainly these arrows, actually, I just mirrored this and I didn't have time to update this. These arrows should be running this direction to the right. But here you can see, and this is one of these infinite strip cells. And I wanted to clarify here, you look at this and you're like, there's nothing infinite about this, like your object is bounded, what are you talking about? But the point is that the vector field goes to 0 magnitude at the red points. So the flow does, is infinite. You can think of these red points as sort of being the infinities on either end. So I wanted to show several orbit complex examples. So this is a simple cylinder model. The purple lines are sort of a very coarse sampling of whales to tell us about the helicing. And blue here, I should say the red and blue faces are singular faces. And the blue curves are the separatrices. And these are two different stripe patterns. So first thing I'll note here is that these cells above and below, sort of the interesting part, these are just annular cells where the stripe level sets kind of just wrap around and are periodic. And then the infinite strip cells here are, maybe it's simpler on this side. The separatrices happen to align. And we have one infinite strip cell here. And then here in cell A and B, where the separatrices don't sort of coincide, you get this split into two different strip cells. And what's interesting to note here is that the integral curves in A do helix with respect to this whale, whereas the ones in B do not. So what you see about the pattern on the left is you have to be lucky or careful with your sampling when you produce the knit graph. If you choose the wrong integral curve to sample, you can still get helicing. In the one on the right, you can sample any one you want, and you'll still end up with something that's helix-free. You could double, triple the resolution of the knit graph, and you'll still end up with something that's helix-free. So and this was in the follow-on work, the 2024 work. We sort of, again, used simple path integral constraints to sort of control this global topology and ensure that there's no helicing of any of the integral curves. Here is a slightly more complex example. I don't have it labeled, but it sort of alternates between annular cells and infinite strip cells. This is a coarse pattern, just so that it's nicely visible, but just another example. A link to our work where there's further details. And if you want a reference for the mathematical specifics, I found this nice book from 1996, and it can give you all the preconditions on the vector field that you need to have this like two types. I've kind of elided some details there. Yeah, and I think what's cool about this is that we actually have like exact helicing now. We can control the foliation structure specifically. And this leaves open the possibility to having a tracing-free pipeline. In particular here, on this bent cylinder, I showed, or essentially if you can do this, you can come up with a vector field where like the actual explicit yarn path will just be an integral curve of the vector field. And here's an example on the left, sort of just illustrated for the bent cylinder. If you follow the arrows, you can see it does trace out the short rows here. And yeah, I know it's a little difficult to read, but I'll just leave it at that. And then also, this is capable of representing sort of a broader range of potential orderings than the AutoKnit case. A very simple example of that is here's a cylinder with two sort of irregularities, and for part of the cylinder, you're actually knitting in sort of like the opposite rotation. So this is impossible to do with a helix-free graph and then a tracing afterwards. Yeah. Okay, so I think I've got 5 minutes for the last thing, which is just how do you place the singularities? I've just been talking about how do you represent them, how do you control the topology, and whatnot. You might ask yourself naturally, how do you place them? So in our latest work, we sort of propose using the curl of the guiding vector field as like sort of a signal and a heuristic to place these. And I call it curl quantization because you can think of it as these irregularities are sort of, as we said, the curl has like integer multiples at these singularities. So you're sort of like representing the curl measure via a bunch of like delta measures sprinkled over your surface. Here it's just the duck, and you can see for the course direction, you can see the curl signal, and it's a little small, but you can see kind of the singularities roughly lying of different types where the curl signal is. Maybe it's a little more obvious in the whale here. Yeah. So the high-level idea is that we discretize the following continuous optimization problem. So the main continuous variable here is this V sigma. This is the vector field that is implied by the spinning form. Essentially, it's the stripe pattern. And what you're trying to do is you're trying to match the normalized time gradient, right? Because that was how the user told you, oh, here's how I want the pattern to look locally. And the other variables here are specifically where do you place the singularities, these curl quantization sites. And this last constraint is sort of specifying that like curl quantization. The curl in particular is a sum of deltas, times the period and some integer, usually plus minus 1. Yeah, I'll note for people who are looking for some sort of nice continuous analog, like this is technically ill-posed. Like if you have curl existing at just a single delta, like this integral will explode and you won't have something well-defined. This is kind of similar to the way that like this vector field design pipeline trivial connections works. Like again, it has no continuous limit. You like refine it and the energy changes. But when you discretize it, you do get something useful out at the end. So it's kind of a similar scenario here. And I'm going to walk through here 2 examples that hopefully give some intuition. This is for the whale direction, the curl of this sort of rotated grad H normalized. And you can see here that the curl is really analogous. You can think of it as being analogous to the Gaussian curvature for quad mesh singularities. For people in that community, oftentimes, you see positive curvature, you throw in a valence 3. You see strong, like negative Gaussian curvature, you put in like a valence 5 or something like that. So really, we notice that curl serves as like a good analog for this. Yeah, and I also wanted to I like this example in particular, of course, because like the Gaussian curvature of the sphere is constant, right? So we can see that the curl and the Gaussian curvature are indeed sort of related but different quantities here in terms of giving you information about where you should place these singularities. Here's an example of the bent cylinder. Note that like along the back spine, I guess you could call it, like it's a much longer path to travel than the interior here. So naturally you'll want to put short rows around the back. And here you can see the curl signal of opposite signs to denote right and left ends of the short rows. And just very quickly, the curl is intuitively, it measures how locally non-integrable the vector field is. And when you have that the magnitude is really high, it sort of indicates a large variation in the spacing of the isolines. So it sort of makes sense to throw in some of these singularities to even it out. And you can sort of see that on the backside here. Yeah, our high-level idea is just we sort of take a iterative, greedy approach to sort of placement and try to place the singularities in high curl regions while accounting for prior placements. And here's just sort of a visualization of the sock model again at like a higher resolution than we've seen previously. And I guess crucial, I didn't write here, but like we maintain the helix-free constraint while doing so. Yeah. And lastly, the last thing I wanted to say about the pipeline is that it's nice in that you can simply use modification of this curl signal to achieve sort of more natural user input than sort of stitch-by-stitch modifications, which has been in prior work. So say you want to mask a region because you want to put some color work or a texture, maybe like a logo or something here. It's very easy to sort of just blank out the curl signal in that region, and you won't place singularities there. Similarly, there are these apparent seams which come about when you place lots of increases or decreases in a row, or maybe a bunch of short rows next to each other. So previously, you would need to specify this like individually, point by point. But if you just sort of amp up the curl measure along that region, the optimization will sort of naturally place singularities in reasonable places. Or it'll achieve some sort of reasonable distribution. Yeah, and I wanted to finish with, clearly there was yet another variable that we could have considered in that continuous optimization problem. What you see here is the basic fertility model. We just did 0 on the bottom, 1 on the top for the Dirichlet constraints, and then we did a naive harmonic interpolation. And you can see that, it ends up getting you a field that varies this way across this arm when really it would make a lot more sense to go along the arm. And this leads to a lot of like uneven spacing at certain points. So obviously you could consider also allowing this guiding vector field to modify itself as well to some degree in order to achieve better spacing. So this is sort of a natural thing to consider. Yeah, and before I pass it on, I don't have a slide for this, but I'll verbalize it. Like here we're looking at this very simple like single jersey pattern. There's all sorts of things on a manifold surface that we don't sort of consider in our particular framework, like non-manifold surfaces, color work, and different knit textures. So Jenny's going to talk about the sort of yarn level representations that take all that into account. Thanks.
Thanks for that. Maybe I'm short. Right, so as Ed mentioned, sort of the previous two abstractions, sort of the fabric level explicitly and the stitch level more implicitly, are sort of operating under this assumption that knitting can be well abstracted as this sort of surface, right? Sort of everything kind of lies within this fabric, so that's the surface. But in practice, yarn is allowed to exist in 3D space. Our objects exist in 3D space. And so as I move on to this sort of like last section of the course, I'll be talking a little bit about how we can use a more low-level sort of yarn level abstraction to capture this. Because if we look at some of the things knitting can do, a lot of sort of like the more interesting technical knits are essentially doing things that start to become pretty non-manifold. So like these sort of actuating examples, they have channels in the structure that were made during fabrication, post-processing wasn't involved, that sort of allows them to sort of like curl and bend. And that gives us sort of like junctures, right, where we can no longer easily represent our knit as a smooth manifold. And I'd like to take a moment to sort of like zoom in on what might be a simple example, right, a pocket. So we have a pocket up here, where essentially what's going on is we have a fabric, it splits, and then it joins back together in order to make the little space where you could put something. And if we look specifically at sort of like the sort of single sheet region, what's going on here is that we have a structure that we call interlock. So I've colored it orange, yellow, and purple to kind of help with the visualization, but this is all supposed to be one continuous yarn, where we start with the yellow stitches going from left to right. So on the right, I have kind of like a top-down cartoon, where when we move left to right, we're sort of like zigzagging between the front and back. But when we turn around, we kind of interleave in between our original set of stitches to kind of create this dense fabric. So you kind of imagine after like doing this a little bit, our sort of purple layer of stitches are sort of sandwiched in between this sort of like yellow and purple layer. And it's sort of like this denser fabric that we can then split to make our more complicated pocket. I think what's interesting is that if we try to sort of represent this interlock structure using the stitch and fabric layer representations captured earlier, we sort of start to run into problems, right? So if we were to try and construct a stitch mesh using the faces that were presented earlier, sort of like the natural ones that contain just a small stitch, we quickly run into this issue where we have these edge connections between faces that want to essentially pass through each other. So it's rapidly not going to work out. We could, of course, cheat a little bit and start introducing new faces that essentially encapsulate a larger chunk of yarn, because, again, this is sort of like how we define these stitch faces. But in order to do this, we end up having to stretch out and distort our underlying geometry. And so what I'll go through, talk about in this section is how we can kind of like consider the underlying graph directly as something embedded in 3D space, and then reason about that as a knit object that we want to fabricate. And perhaps another interesting point is that even if you wish to fabricate something that is manifold, this issue of yarn being something that exists in 3D space can still come back to bite you. So I have up here sort of a picture of a knit graph that's supposed to represent a two-color tube. So like imagine like a barber pole, two colors sort of striped up the side of it. And if you were to take this knit graph and kind of push it through an existing compiler, you'll get this pinched lemniscate structure instead, right? Where essentially what's going on is that the way the knitting machine works, right, is that it exists in 3D. We have these two needle layers, but we also have the yarn that kind of exists in the space between them and has to move between the two layers as you undergo the fabrication process. So if you're not careful in how you sort of translate your more high-level structures down to low-level instructions, you're going to run into errors like this. And so this was sort of the motivation behind a series of papers on coming up with a topological semantics for knitting. So the idea is that we have these knitting programs, they have meanings that are the objects we're trying to make, and we're trying to approach this from a low-level yarn topology perspective. So this has been done with a bunch of cool people at various institutions. So I'd like to start with just sort of a brief reminder about what knitting is, because I feel like I'm constantly underestimating how much other people don't know about the thing I've spent my whole PhD on. But just as a reminder, so knitting, you have yarn, you form it into loops, they pull through each other, and of course you have decisions about how you can make this pull through, right? So for example, even if you only had these two loops in consideration, you could either pull it from back to front to make a front knit, or front to back to make a back knit. If you know knitting, this is knit and purl, but I will open that can of worms only during the coffee session. So what's interesting is that by using different mixtures of these front and back knits, not only do you get a very different visual look to your fabric, but this also affects the underlying material property. So you can see that these examples, even though they all use the same number of stitches and the same aspect ratio, they have very different sort of rest configurations as well as like interesting kind of curling at the edges. And so essentially the point I'm making here is that these high-level material properties depend on our low-level stitch topology. And what's also interesting is that if we think about knitting, it is something elastic, right? It's soft, we can stretch and squash it. If I had a hat and I put it on my head, it would still be a hat, right? But there's another soft elastic deformation that we can undergo, which is that if I were to grab a loose end of the yarn and start pulling and unraveling, right, eventually we'd agree that like this would not be the same object anymore, right? We would consider some elastic deformations to be destructive. And so when we move into trying to formalize the topology of knit objects, one thing we need to keep in mind is that while some deformations are valid, others are destructive, and we need our notion of correctness to consider this. So how should we formalize the topology of knitting as yarn? Well, there's this area of math that some of you might be familiar with, pretty old. It's knot theory. So it's the study of loops embedded in R3, where we consider two knots to be equivalent under ambient isotopy. So essentially, if you take your loop and smoothly deform it without ever causing any interpenetrations, they're equivalent if you can move between the two presentations without having to pierce through. So the complicated knot on the right is equivalent to the unknot. The trefoil knot on the left is not equivalent to the unknot. And so we see something that's a little bit yarn-like. We're smoothly deforming it. We might think that knots are the mathematical object that we should be using to represent knitting. But as it turns out, we can't directly do that because these loops have no loose ends, right? Our physical object has a loose end that I can just grab and pull. If we were to use knots directly, we wouldn't be able to capture this. But there is something kind of interesting here that I'd kind of like to emphasize for a bit, which is that when we're working with these topological mappings, we do have some sort of like flexibility in how we define things. So for example, one topological mapping that we might think makes sense is just homeomorphism between two objects, so whether there's a continuous invertible mapping between them. But directly doing this is going to be too loose if we're just kind of concerned with like how objects sit in space, right? So the idea is that if we had the trefoil knot and the unknot, they would be homeomorphic with each other, because the idea is that from the perspective of like a local point, it has a continuous neighborhood with any other point in the other object. And so what ambient isotopy is saying more precisely is that the objects we care about are embedded in this ambient space, and it is that ambient space which needs to have a sequence of homeomorphisms that sort of carry one object to the other. And it's sort of under this definition that we can then capture the fact that our object that we care about doesn't interpenetrate with each other. And so I think one thing that's kind of interesting is that, well, we could always just sort of change our idea of our ambient space and see if that helps. So there's a slightly newer mathematical object known as the tangle. The idea is that instead of being embedded in R3, we're sort of embedded in a topological ball instead. So it's sphere-like with a distinguished boundary. And the idea is that now you can take your loose ends and you can essentially stick them on this boundary and have that be sort of like constrained and distinguished. So when it comes to equivalence on tangles, remember ambient isotopy is essentially deforming the embedding space and carrying along the sort of like tangle with it. So we're fine to kind of like squish and deform our embedding space. But one thing we have to be careful of is that because we have this distinguished equator, if we deform it too far and we push these points through each other, this no longer counts as a sequence of homeomorphisms. So we have to make sure that the order of our endpoints on the boundary remain the same as we perform these transformations. And so these tangles are really helpful because now we have endpoints. I was complaining about how knitting needs us to track the endpoints. But as it turns out, tangles are both over and under constrained for our problem of formalizing knitting. So the fact that everything within the tangle's internals is allowed to sort of smush around as we wish means that there's certain semantic features inside of knitting that we can't sort of like keep track of. Meanwhile, the fact that we have to kind of commit to this ordering of endpoints on the boundary for this tangle means that you're sort of like overcommitting. You kind of have to take your knit object and sort of pin it down in the real world, which is often not what we do. So as sort of like part of this work, my co-authors and I made this observation that embedding sort of like this constraining space was really helpful, so we might as well just continue embedding constraining spaces in something we called a fence tangle. This is part of a paper that was presented at SIGGRAPH, where essentially these embedded fences have a similar constraint that prevents any endpoints that pass through them from being allowed to pass through each other. I just realized I haven't actually been using this at all, but there's a pointer. So you can see that this loop down here, pointed at by blue, in the tangle paradigm, it would be allowed to essentially untwist with this sort of red strand, and this would allow this pair of stitches to unravel. But if we have instead these embedding fences, then this transformation would not be considered equivalent under ambient isotopy. And so this ends up being sort of like the topological object we propose for representing knitting. The other cool thing is that you can do composition with them. So the idea is that you can deform your ball into a slab, and then you can glue your slabs together with horizontal composition, where you kind of glue along the empty edge. This is always allowed. You can also do vertical composition, where you sort of compose from the top and bottom. One thing here is that vertical composition requires compatible boundaries, where it has the same number of strands crossing, where if they are mismatched, then you would have a loose strand kind of floating around in the eternal, and that's sort of not allowed the way we define it. And so this idea that now we've come up with this mathematical domain of what knitting machine programs means, we can now start establishing a semantic function where we go from specific knit out programs to specific fence tangles. And then when we examine whether a program rewrite or transformation actually preserves equivalence or is correct, we can look at the underlying fence tangle and appeal to that, topologically speaking. So I've talked a lot about sort of mathematically what it is we'd like to work with. So I'm now going to take a little bit of time to kind of talk about the formal knit-out program, just to provide context for the types of things we have to be concerned about when defining this semantic function. So just to bring this picture back, knitting program's a little bit miserable, pretty uninterpretable, just a whole bunch of pixels that someone painstakingly made in MS Paint. As it turns out, there's a slightly different low-level language that's more akin to sort of just a list of the ordered descriptions of operations we can perform. So we call this language knitout. So I've got a really short program here where the first operation is doing what we call knit. It's essentially referencing a specific needle, F1, and telling it to grab the carrier, 1 in purple, and pull it through its loop. There are other types of operations we can tell needles to do. For example, we can tell it to tuck, in which case instead of pulling through, it will just form a new loop that's stacked on existing ones. We can do things like tell the carrier to move past a specific needle without actually actuating that needle. We can also just tell a needle to drop whatever it's holding. There's 5 additional operations, which I won't get into because this is not a class about teaching you how to actually write these programs. But I was just trying to illustrate essentially 2 big things that come up when we reason about what these operations are doing. The first is that most of these knitting machine operations are very local. So you can see that these operations will call a specific needle, and it will cause essentially a very small change in topology. You're making 1 loop perhaps in this new area. But despite that, we still care a lot about the uninteresting topology, where nothing has necessarily changed, right? If I show you an object that is only like 3 loops wide versus 5 loops wide, those would be different from each other. So essentially, the semantics does depend on the underlying state of the machine. And perhaps even more tricky is that the way the knitting languages are specified is that there's additional state dependence, where because these operations are describing what the machine should do, depending on how the machine initially is before that operation is called, you can get very different topology. So you can see that in this example, these are 2 diagrams taken from sort of one of the first knitting semantics paper, where they had to draw 2 of them because depending on whether the carrier starts to the left or the right of the needle that you're using, you're going to get very different sort of end topologies here. So you can see this picture looks different from this picture. And so because of this, when coming up with sort of this denotational semantics where you want programs to mean specific mathematical objects, we have to essentially introduce these additional validity constraints. So there's a lot of variables and math on this slide that you should not worry too much about trying to understand. All you really need to take away from this is that we have this type relation where you have some initial state, you have a program snippet that you call on that state, and then you have some end state, where in order to be valid, there's some set of preconditions that must be true. So you need your carriers to all be in the right place, you need your needles to have loops to knit with, and then once you've executed this operation, you'll result in some known end state. So you know where your carriers will stop, and you know the new number of loops on your needle. And the idea is that when we work with this more sort of strict definition of a knitting operation, we can start constructing these templated diagrams that define the class of fence tangles that a given operation maps to. So here, the knit operation denotes this class of fence tangles where it's a composition of the identities where not much is happening with a more complex class of fence tangle in the center. And so we can define sort of these denotation functions for all of the operations that appear in this language, as well as this additional validity relation that just says that if we have 2 program traces that are valid and share an intermediate state, then we know that the concatenated program is also valid. And so when we now come to this problem of seeing what a specific program denotes, we need to know what the initial state is. So for example, here it's just saying that front needle 1 has a loop, back needle 2 has a loop, and our yarn carrier is at position 3. And so then given an operation, we know what the end state will be, and we'll know the specific fence tangle that corresponds to. We can then continue with the second operation, and so long as that also denotes a valid subprogram, they concatenate, and we know that our program concatenation maps to valid fence tangle composition. What's really interesting is that even at this level where we're working just with like operations and diagrams, we can already start to develop the framework that will allow us to sort of optimize and rewrite our programs. So here on screen, I've got just a single generic fence tangle horizontally concatenated with the identity. We can see that we've vertically concatenated with a second fence tangle. And hopefully it is clear that even though we don't know anything about the contents of K1 and K2, if you slide K1 up and K2 down, these two should be equivalent. There's no point where the strands would ever need to kind of move through each other. And so this allows us to prove general lemmas about fence tangle equivalence that can then apply to program rewrites. So when we move operations around, if we know that they happen to respect certain preconditions, we'll just know that they always preserve the underlying fence tangle equivalence. And this in turn allows us to do practical things like improve the fabrication time. So essentially, whenever we show these sort of like pixel diagrams of these knit programs, the vertical height represents time. So longer programs takes longer to run. But if you rearrange the operations, the machine can essentially clump them together and run the whole thing more quickly. We can also do things like change the amount of space it takes on a machine. So we can rewrite this pleated tube to take up fewer needles, and do things like remove spurious operations that would potentially cause errors. So this formal semantics allows us to sort of have a formal mathematical meaning for any given valid program, and that in turn enables us to rewrite these programs to sort of be more optimal given our use case. Kind of followed along? Okay, cool. So I just spent a long time talking about program semantics. I pointed at some MS Paint pictures and said, this is miserable, and then showed you a whole bunch of text and said, clearly this is better. You're probably thinking, no, it isn't. Wouldn't it be great if we had some, again, geometric representation of the object we had some compiler that just took it in. Maybe this rewrite stuff can come up with the optimizing step, I don't know. And then we just got the result that we wanted. And indeed, that is what this new representation called the instruction graph helps with. So this was presented at SIGGRAPH Asia last year, where sort of similar to the idea of the original knit graph that was brought up before, our nodes are essentially representing stitches very loosely, but specifically these nodes are oriented boxes with inputs and outputs, where what they sort of denote is again sort of a sub-fence tangle. We also have specific types of these directed edges that connect our nodes. So these sort of represent the routing of the loops and yarns in space. So we can see that sort of that between the graph on the left and the denoted fence tangle on the right. And the thing that's really sort of differentiates this from the existing knit graph is that the embedding of this graph in 3D space is very important. Sort of as these edges and nodes sort of twist in space, this affects the denoted fence tangle. And so this is great. It'd be nice if we could then do what I showed on that slide, just compile from the instruction graph down to formal knit out. But as it turns out, this is slightly complicated, as I'll show from this little semantics diagram. So again, just as a reminder, semantic function, we go from some representation down to the mathematical object that it means. And if we look at the entire space of just sort of all valid knit out programs, this gives us a slightly different definition of knittability than what was defined before. It's just literally the subset of all fence tangles that a valid knitting program can denote. In contrast, instruction graphs will also denote some subset of the fence tangles, but depending on how they intersect, they may or may not actually denote things that we can fabricate on the machine. So they just might denote something with like totally nonsensical topology that we can't actually realize. And so to actually allow us to perform this compilation as we wish, we need to understand the relationship between these two semantic domains. So this ends up kind of falling out into two subproofs that are talked about in the paper. The first is that given a valid machine knitting program, there exists some equivalent instruction graph that will denote the same thing. This is what we call sort of lifting our program back into the instruction graph. This ends up being pretty trivial to describe, essentially the same way that we sort of defined the class of diagrams that a given statement corresponds to, fence tangle diagrams. We can also define the class of instruction graphs that a knitting operation also corresponds to. So it's just a bunch of diagrams. You stare at the diagrams and believe that they're the same. But it turns out the opposite direction is quite complicated because it's quite trivial to construct some graph that makes something that just cannot be machine knit. However, essentially, by staring very hard at the class of machine knittable instruction graphs, we noticed that given a certain set of graph embedding properties, we can prove that every instruction graph that we call UFO will have an equivalent formal knit out program. So I'll slide very fast towards what UFO is, just an intuitive level, but I think the big takeaways is that these are sort of topological embedding properties that happen to also correspond to constraints on the machine. So sort of as was gestured at before, you cannot knit through a loop that you haven't already knit through, so you have to kind of maintain a consistent ordering throughout your graph. So knitting machine operations are performed sequentially. If we establish a time axis within our embedding space, then the operations have to sort of be aligned with that time axis. There's also the fact that the knitting machine cannot introduce arbitrary twist into loops, so we have to make sure that kind of given a sort of point of view access, that these graphs are also properly aligned so that there's no arbitrary twists being introduced. There's constraints on sort of how the yarn carriers can introduce yarn to the machine. So the first thing is that a carrier cannot be in two locations at the same time. So sort of along the time axis, given a labeling of which carrier is used in for each part of the graph, we have to make sure that they're unique along our time axis. And then finally, again, the machine sort of has constraints on how it can twist things around each other, so it can't introduce arbitrary twist. And so essentially the way this comes out as a graph property is if two arcs cross each other, their crossing order has to be consistent with their carrier ID. And so again, these are just sort of like a set of graph embedding properties that are relatively trivial to check for. The idea then being that once we have a UFO instruction graph, we can partition it into what we call sort of these single event partial graphs. And then we have a compilation algorithm for lowering each of these partial graphs to a small program. I think the main thing to point out here is that it lowers to a program and that it's multiple statements, but we know what that lowering function is, where we just had to make sure that this lowering function always preserves topological equivalence, while also making sure that the composition of these subprograms will always be valid. And so yeah, just kind of as a summary, we have this representation of knitting sort of at this intermediate stitch/yarn level. Once we have that, we do need to transform it into an upward-forward ordered presentation, so we can do that under ambient isotopy in order to make sure that the underlying fence tangle topology has been preserved. But once we do that, we always know that there exists some program that will always create the same topologically equivalent program, and from there we can fabricate it and get our desired result and know that it is topologically equivalent. So some interesting things kind of related to that. I said that we have some input object, we somehow transform it under ambient isotopy in order to get something that's UFO, and then we can compile it. There are some interesting questions about whether such a transformation even exists. There are certain things that are obvious to check for example, cyclical dependencies, but there are some more complicated nuances that sort of remain as an open question as to whether there even exists a UFO presentation at all. And just sort of like another interesting thing is that I've talked a lot today about fence tangles and why they're pretty good as a semantic domain, but they also have their issues. It's very difficult to generally verify the equivalence between two fence tangles, but there are other mathematical objects that are a little bit easier to compute on. So there's a question here about whether we can find something that can represent all of knitting and all of the equivalences that we care about, or if we have to sort of like find other ways to reason about program equivalence. So yeah, it's a memory slide that I'll move past really fast because I want to come back to this really good picture. So I talked a lot, well, we all talked a lot today about how it's useful to think of knitting at these different levels of abstraction, right? Where we have knitting sort of as fabric, as stitches, and as yarn. And if we take yet another step back, this actually aligns kind of nicely with how fabrication works in general. Often you will start with some high-level general idea of what you want to make, and then you have to translate that from some design specification into a program. May or may not be you who did both the design and the program. Then it's very likely that the program that you wrote isn't going to be directly run by the machine. It'll have to be compiled to these low-level instructions, and only then do we get to see the output of it. And so if we work really hard, we can kind of squish our three different representations into these three parts of this fabrication pipeline. But of course, these aren't actually siloed off into independent bins that don't talk with each other. It's really useful to be able to have information kind of flow back up this design pipeline. And sort of even independent of these specific computational representations, I feel what often happens is that you make the object, you look at it, and you're like, this isn't exactly what I wanted. I need some way to modify my design or my program to get closer to my actual stated goal. And similarly, it might be nice if instead of having to wait until you've actually made the object, you could maybe simulate the object and see a little bit sooner what's going on here. And so there's a lot of interesting open problems about the best way we can go about sort of like dealing with these parts of the design pipeline in a way that's amenable to knitting. So as was briefly talked about before, in simulation, we've already had this history of simulating knitting as either yarn or fabrics, but there's been a lot of recent work on trying to do this sort of at the stitch level. So this is sort of upcoming stuff at SIGGRAPH this year. Another interesting question is how we can actually computationally capture a physical object and then incorporate that information back into the design pipeline. So the idea is that we do have some existing work on how we can capture knits for simulation and occasionally program generation, but these pipelines are very constrained. They require you to kind of have a small flat patch of knitting that you already know some measurement information about. And so there also exists a lot of potential work here on how we can sort of improve this capture process. But the thing about knitting is, again, it's soft and elastic, and that comes into play a lot when it comes to the design process. So in the upper left over here, I've got two knit Stanford bunnies. You can see that they look quite different. But the issue here isn't that the surfaces are particularly different, but the fact that what's stuffed inside of them is. So up here, we kind of have this sort of rigid Stanford bunny. The knit skin was carefully stretched over it. But down here, we have stuffing. So it's just stuffed inside like a stuffed animal. And you can see that because of how that stuffing fills the bunny, the two of them look quite different. And so there's been some work on how we can sort of incorporate this idea of the elasticity of the knit into the design process. So up here is a work that was on how to sort of control the elasticity of the knit, because this is something you can program in based on the stitch pattern. This is crochet, not knitting. But it is a soft fabric that was stuffed, and this has some interesting insights about how the curvature of the object affects how well the object can be realized when you stuff it using some stuffing. And of course, there's other things you care about when you're designing fabric, right? You might not have it stretched over a form, but instead draping off of a figure, right? And so this is another place where figuring out how we can characterize that, simulate that, reason about that in the design process would be really helpful moving forward. Finally, as was kind of like gestured out throughout the talk, these different representations are useful for how we reason about knitting, but they also should ideally talk to each other, right? There are some interesting insights in how the high-level quad layout view of knitting could be combined with the low-level singularity placement in order to get better knit stitch layouts in general, as well as how these sort of more high-level general criteria have information and degrees of freedom that would be useful for the low-level compilation side of things that should be translated along the design pipeline, as well as the low-level sort of like more detailed topology having information about fabricability and other design considerations that should ideally be passed back to the initial design input. And this is really important because there's a lot of really cool things that knitting can do that essentially we don't have general computational tools for yet because they incorporate all these different aspects of low-level topology, high-level surfaces, as well as like stitch placement, where if we could build better tools, everyone could make cool things like socks that know where you're stepping and cool knitting illusions. So we will release these slides with even more references. You may ask questions now. Or you can all get coffee, I don't know. Oh.
Hello, thank you for the presentation. Really interesting. I have a question about scalability. It's difficult for me to know how the method that he presented here can scale. I'm talking about the computational time, a bit, what is the complexity of what I do
I mean,
Yeah, I can speak for the stitch level abstractions. Yeah, actually, so I had a slide with the table of runtimes, but unfortunately I deleted it. I think what that slide had is the initial like helix-free stripes, like the graph 23 paper, was actually this enormous. I'm not like directly answering your question here, but like there was this big mixed integer problem because you had an integer variable for every single face of the mesh to specify whether you wanted a singularity there or not. That was obviously like enormously computationally expensive. But with this sort of sorry, thank you. With the iterative approach, I think it led to a speed up of like, I don't know, 10 to 100 times typically. The way that works is, although it can still be rather lengthy, depending on the size of the model. Essentially, it's checking for these pairs of singularity placements, and it's checking if it's like decreasing sort of like the overall objective in each step. So oftentimes it can check many candidates. So yeah, I'm sorry, I actually don't have it off the top of my head, the timings, but it's not quite like the duck model. I think probably took like half an hour or something. So it did take quite some time. Yeah, we are working on a different method, which is more globally informed, but that's future work, I guess. Yeah, that's not this iterative process. Yeah. Yeah. Thanks for the question.
yeah, I can also add a little bit in that it's probably useful context in that the amount of time it would have taken to fabricate that duck was also kind of on the order of like maybe 30 minutes, right? And so ideally it would be faster than that, right? But also you are saving yourself time if you do it right the first time instead of having to wait, see the duck fail, and then try again. I went back to this slide because basically all of this, except for the one in the middle, is like pure theory. You can theoretically prove whether two things are equivalent, and we kind of built sort of like user interfaces to help you kind of like pictorially move through proofs of equivalence for specific examples. But those interfaces were not good. They were mostly just kind of to like prove as a proof of concept that it's useful. One thing I'm kind of excited about is that this last one is still very theoretical in that we have a polynomial time proof, but it's a polynomial time proof, not something that actually runs fast enough. But it is getting general, and so I think there's like some interesting hope here about getting us to the point where like we can compile things fast enough to actually make it part of a pipeline. Yeah.
Yeah, and I can speak briefly on the design scale time frame. So if you're talking about polynomial time, I said we have an SMT solver, so that's naturally just NP complete. You might think that's terrible, but it actually scales with the number of patches of fabric. And so if you're able to get kind of this quad layout level of granularity, you can, it's milliseconds to solve the design problem. If you want to use the SMT solver to actually solve for the stitches, that's where it gets dicey, but that's where we use a better formulation like Ed has instead. So our computation times were up to about 10 minutes, 15 minutes to get the most complicated patterns that we did to the stitch patterns, but the design patterns were sub-second.
Yeah, it also occurs to me that like maybe a useful frame of reference is this is a small knit guy. This is a little bit on like it's coarser than your t-shirts, right? But it's not horrifically coarse like the big chunky things you might do by hand. I would say this is like about 1,000-ish or so stitches, even for this like small thing. So if you were trying to do things at the stitch level for like a reasonable human-sized garment using like material about this coarse, like these existing methods are a little bit too blunt of a hammer. So this is sort of another area where I think there's like interesting future work potentially.
Question. You mentioned in the very beginning these whole garment knitting machines. I was wondering what the principal topological constraints are and what they can produce. Is it something like genus 1 with boundary, or
Yeah. So I did have a slide up there on like Morse decomposition. So like if you look at the time function and you split it at like the critical level sets, you get this like tubes and sheets decomposition. And this is from ModernKnit, but they sort of characterized it as your surface is knittable if it has a planar read graph representation. And this is because like when you have the tubes on the machines that we have like, it's a linear bed of needles, or two opposing linear beds of needles, and the tubes have to like be ordered on them. So you can't kind of like pass the tube, like one tube through another, essentially. So you have to be able to like order them. I've actually like, there's part of me that's a little like unclear on like the exactness of it, because the example that I've seen that's not knittable is like, I guess it's like a genus 2 surface, but you're trying to like swap two of the tubes. Like, I think strictly at a topological level, I think that's still homeomorphic to like maybe a more standard shape of the same genus, but somehow the geometric embedding like matters there.
Yeah, I zipped over to this slide after changing my mind about going back to the other slide with the sort of non-manifold junction, because sort of like if you go down to the yarn level and then go all the way to topology where things can just stretch infinitely, then you have all the freedom in the world to just sort of like draw your surface by kind of curving the yarn through it and sort of like peeking through gaps and moving things around. Of course, in practice, we do not live in a world with infinitely stretchy yarn. So essentially, one of the major constraints about building more complex sort of like topological surfaces is that if you want to have layers of fabric that then need to merge together, you can do this by essentially carefully spreading them out along the machine so that none of them actually intertangle with each other. So even though like you're looking at them and they're sort of like stacked on top of each other, because none of them actually interlink, they're still separate, and you can kind of like gently jiggle them and sort of rotate them. It's all very miserable and painful, but you could in theory do it. But the point that I thought maybe this slide might illuminate is that when you do this, you have to kind of stretch everything out. And so this this pleated tube structure on the left is kind of neat because it has these folds, right, which were places where fabric were stacked on top of each other on the machine but kept separate. And we can see that in this example, it looks very loose and kind of lacy, and this one is slightly less loose and lacy. And so the idea is that kind of like up to a limit, you can kind of start packing things together, but eventually you kind of run out of space on the machine, and you kind of have to keep things spread out, and this is going to make your fabric look more open and airy. And so in theory, you can push this pretty far, but in practice, you're going to run into like the limits of the machine, as well as the fact that it's very miserable like trying to program these in a way that keeps these sheets from intertangling. There's been some interesting work on sort of like alternative knit programming languages that are sort of like reasoning about things at this sort of like sheet juggling level, which I think is kind of neat. But yeah, it kind of depends on where you say, oh, this is no longer physically plausible. Because the original sort of AutoKnit work was taking a somewhat conservative stance of like, okay, we're going to forbid anything that's like too complicated and that we don't know how to perform the compilation of. And so it's a lot more restricted on sort of like the genus of surfaces that you can construct.